The simplest resistivity tools are set up to introduce a circuit between the borehole and the surface. Point A is the source electrode, and point B is the current return in this illustration. The potential drop is then measured between the borehole and the surface. Points M on the tool and N at the surface in this illustration. Knowledge of the geometry of the system permits conversion of a voltage drop into resistivity. Our assumption is that the current radiates spherically out from the source in the borehole, equally in all directions, and our intent is to measure the voltage here at the measure electrode and compare it to here at the surface. In order to measure the voltage change, we will have to rely on integral calculus to help us obtain the voltage change with respect to distance from the current source. This change is referred to as dV over dr, where little r now signifies radius and not resistance.
Since the area of a sphere is 4 pi r squared, we substitute this for area A and substitute little r for the length L. Rearranging our terms and integrating dV over dr will result in V equals IR over 4 pi AM, where AM is the distance between downhole current and voltage electrodes. Therefore, in our simple model, the geometry constant of our equation is tool-dependent and is not dependent on downhole factors. But the basis of our result hinges on the acceptance of the spherical current radiation model.
In general, current flow can be characterized as flowing away from the source through the borehole and rock of semi-uniform resistivity and being collected by the return electrode.
This means that the resistivity measured by a logging tool primarily reflects the combined resistivity of the mud, R sub m, the resistivity of the invaded zone, R sub xo, and the resistivity of the rock, R sub t, in the near vicinity of the electrical source. In the configuration we examined, the resistivity logging tool is called a normal device, with a spacing represented by the distance from electrode A to electrode M. By rearranging the system such that point N is now downhole, the logging tool designation becomes a lateral device, with spacing represented by the distance between the current source electrode A and imaginary point O, representing the midpoint of electrodes M and N.
There is a common difficulty encountered by simple normal and lateral resistivity devices suspended in the borehole.
Very conductive mud can short-circuit the logging current such that the resistivity of the formation is not sufficiently represented.
Modern electrical logging devices commonly avoid the problems associated with very conductive muds by focusing the electrical current laterally into the formation. This lateral focusing is done with currents generated by the nearby electrodes on the tool.